We, Group 10, will now present our study entitled, Design and Simulation of a Digital Gas Leak Monitoring and Alarm Control System using Verilog and VHDL, together with its Verilog implementation, RTL schematic, and ISIM simulation. I will now present the Verilog implementation, RTL schematic, and ISIM simulation of the system. The VHDL code defines the behavior of the gas monitoring system. The system has three inputs: clock, reset, and a 2-bit gas level signal. The gas level represents different conditions such as safe, warning, dangerous, and critical. The outputs include the safe LED, warning LED, alarm, shutoff valve, and a 2-bit status signal. The main logic is implemented using an always block triggered at the positive edge of the clock or reset, making the system a synchronous sequential circuit. When the reset is activated, all outputs are turned off, ensuring the system starts in a safe state. The system uses a case statement to determine the output based on the gas level input. When the gas level is 00, the system is safe, and the safe LED is activated. When the gas level is 01, the warning LED is activated. When the gas level is 10, the alarm and shutoff valve are activated. When the gas level is 11, multiple outputs are activated, indicating a critical condition. The VHDL code represents the behavioral design of the gas monitoring system. It defines how the system responds to different input conditions using sequential logic. The entity gas_monitor_system declares the input and output ports of the system. The inputs include the clock signal CLK, reset signal reset, and a 2-bit gas level signal gas_level. The outputs include safe_LED, warning_LED, alarm, shutoff_valve, and a 2-bit status signal. The architecture behavioral contains the main logic of the system, which is implemented using a process block sensitive to the clock and reset signals. Inside the process, the system first checks the reset condition. When the reset signal is equal to 1 foot, all outputs are set to 0. This ensures that the system starts in a safe and initialized state. When the reset is inactive, the system operates based on the rising edge of the clock signal. This makes the design a synchronous sequential circuit, where outputs only update during the clock transition. A case statement is used to evaluate the value of the gas level input. Each gas level corresponds to a specific condition. When the gas level is 00, the system is in a safe condition, and only the safe LED is activated. When the gas level is 01, the system enters a warning condition, and the warning LED is activated. When the gas level is 10, the system detects a dangerous condition, activating both the alarm and shutoff valve. When the gas level is 11 inches, the system enters a critical condition, where multiple outputs are activated simultaneously. The status output reflects the current gas condition based on the input value. This schematic shows the RTL or register transfer level representation of the VHDL gas monitoring system. On the left side are the input signals, which include the gas level, clock, and reset. These inputs control the system and determine its operation. On the right side are the output signals, such as status, alarm, safe LED, shutoff valve, and warning LED. These outputs represent the response of the system based on the gas level input. The internal connections in the schematic represent the hardware logic generated from the VHDL code. This confirms that the design was correctly translated into a hardware-level structure. This slide shows the ISIM simulation of the VHDL gas monitoring system. At the beginning of the simulation, the reset signal is activated to initialize the system. During this stage, all outputs remain inactive, which confirms that the system starts in a known and safe state. After the reset is released, the gas level input changes sequentially to represent different conditions such as safe, warning, dangerous, and critical states. The waveform shows that the outputs respond correctly based on the applied input values. When the gas level is set to 00, the system activates the safe LED, indicating a normal condition. When the gas level changes to 01, the warning LED is activated. For 10, the alarm and shutoff valve are turned on, representing a dangerous gas condition. When the gas level becomes 11, multiple outputs are activated, indicating a critical state. The waveform also shows that the outputs only change at the rising edge of the clock signal. This confirms that the system is operating as a synchronous sequential circuit.